right, waves. Waves. So this is our fourth standard. This is one of the big ones. There's a lot of ideas in here because this is how energy propagates. You know, heat is one way energy goes from one place to another. But another way is waves. Waves is one of those things, is the way a lot of energy moves from place to place. Sound, light, earthquakes, all this stuff, it's all energy. Energy moves through the ocean in a form of heat and in waves. And a wave is energy moving. That's what a wave is. When you see a wave is the manifestation of the energy. Basically, it's about the only way you can kind of see energy is a wave. Like if you look at the ocean, you see that wave going by on that. In a wave, the energy moves. The energy moves, not the thing that carries the energy. Not the thing that carries the energy. Yes?
So water's not moving?
There's a caveat to that. Let me add to that. No net movement. In other words, the medium will always return back to its original point. Yes, the medium moves. It's like with a transverse wave. It goes up, it goes down, it'll come back to its original position. With rarefactions and compressions, they'll move. The ocean wave does move. Now, we're actually going to talk about what happens when these waves get close to shore, because there's something else. You know, as we know, when we talk about this, we kind of take the broad view. Well, when it gets toward the shore, that gets a little more complicated. But we'll talk about why the water near the shore moves, because there's some other things coming in effect. But for the most part, what we're talking about, it's the energy. The energy is what's moving, not the medium. Medium, in other words, what we're saying is, if I plunk down a rock here, or put my finger in the water here, the wave moves out there. Now, is the water that's underneath my finger, is it moving and carrying that energy way over there like convection does? No. The wave moves. The energy moves through the wave. And we can especially see that when we start talking about our springs. And energy moves through three different kinds of waves. There are three different kinds of waves. There are transverse waves, longitudinal waves, and surface waves. Surface waves. Anyone need more time on this one? Let us continue. So, when we talk about waves, we're talking about periodic motion. That would be like my pendulum here. Let's look at the pendulum. Pendulum goes back. It keeps repeating. The motion is repeated over and over again. Same thing with a wave. You get the wave repeats over and over again. In fact, at the very beginning of your book, it shows a picture there of the guy who basically is the founder of the Exploratorium. It has a pendulum with a pen on it, and when he rotates that piece of paper underneath, you notice he gets a wave. It's basically a sine wave on that. But there's some terminology. This is where that picture there on page 374 comes in. So if you want to get ahead, you can start drawing that picture, because we're going to put some information on that picture. Anyone need more time? So, wavelength. So we have our wave here, and there are some terms, and especially transverse and surface waves have kind of the same terminology. There's a couple of things we need to add for a longitudinal, but some things. Wavelength. We use the Greek letter lambda. This is the Greek letter lambda as our symbol, lowercase lambda. We measure it in meters. And it's the distance between successive similar parts of a wave. Similar successive parts of a wave. In other words, they show you here, like here, they go from a crest to the next crest. We could go from a trough, which is this low point, to the next trough. Notice they picked this point, and they picked the next time it got to that point down there is a wavelength. So successive wavelengths. All right, we also have the amplitude. The amplitude, sometimes we use a symbol of x, and this is also in meters. And this is the displacement from 0. Another word for that would be rest. And this has to do with how much energy. How much energy on that? How much energy? Okay, so if 0 is in the middle, how far? Now there's another term of total displacement. Total displacement would be like from the crest to the trough. But in like a longitudinal wave, it'll be how much does it compress or how much does it rarefact. But not total displacement. How much energy? In other words, the greater the amplitude, the more energy. So like in sound, a louder sound would have a greater amplitude. A brighter light would have a greater amplitude. But the amplitude has no effect on wavelength. The amplitude, no matter what the amplitude is, it does not affect wavelength, it does not affect wave speed. Basically, it's how much energy is that particular wave carrying. But it has nothing to do with how fast it's going or what the wavelength and frequency are. It doesn't anything that just tells you how much energy. And the more the amplitude, the more energy is in the particular wave on that. With sound, it would be loudness. With light, it would be brightness. Anyone need more time? It's set up a little bit longer this year. Usually it's the Santa Anas that hide just sat there. It didn't move. It's kind of like, and it caused basically the stalling. That's why they had all the cold weather in the east too, because everything just kind of stopped. You know, a stalled front. They stop. Weather. Gotta love it. All right, frequency and period. We've seen these words before, but this time we're going to look at them as, you'll notice where frequency is the number of events per time, we're actually going to define the number of wavelengths in a length of time. So how many waves pass by in a length of time? It's still an F in hertz, right, HZ. Period. Now this is very important because period is the time for one wavelength. That doesn't matter what wavelength. You know, if one wavelength goes by, that was one period. One wavelength will go by in one period of time. Whatever that time happens to be, and whatever the distance of that wavelength, that wave passes by in one period. You know, it's kind of one of those, how we define it. Still T in seconds, and we still have that relationship of T equals 1 over F, and F equals 1 over T. I mean, that was from way back there, about chapter 9, 10, 11, we saw that unit. Now the wave velocity. So our wave velocity equals wavelength times frequency, which means it's also going to be wavelength divided by the period. So symbolically, V equals lambda F, or lambda over the period. We usually use that. Most of the time you're going to see lambda F. Wavelength times frequency. Now the thing is, when you're solving these kind of problems, we're using them, velocity is treated as a constant. In other words, for whatever environmental conditions are present that dictate the velocity of that wave, we will treat it as a constant, which means we would say the velocity is not going to change. So if there's any change in wavelength, is going to cause a change in frequency. So if wavelength goes up, frequency goes down. If wavelength goes down, frequency goes up. And it's going to be the wavelength that changes here. The wavelength. The wavelength is going to change on that. And you've experienced this sort of thing. In air, temperature is pretty much the deciding factor for speed of sound in air, is the temperature. Higher temperature, faster, lower temperature, slower. But you've experienced changes in frequency and wavelength anytime you go to a crossing and you're waiting for the train. When a train goes by, does the train horn sound the same the whole way by you? It sounds different on one side than it does on the other because it's going to change. It's the Doppler effect. The wavelength changes because of how the train is moving and causes a change in the frequency. We'll go over the Doppler effect later on. Anyone need more time on this? So let's talk about the three types of waves. Transverse waves. Transverse waves. The wave moves at a right angle, transverse to the direction of motion to the energy. These are also called shear waves. That transverse is called a shear. Thing is, transverse waves will only go through solids and we'll talk about, there's an exception to that. And our example is secondary earthquake waves. Secondary earthquake waves can only go through a solid. They cannot go through a liquid and they can't go through a gas. Because they need something basically to return the energy. They push on and Newton's third law thing is going to push back. Liquids and gases cannot push back. They would not be able to push back because they don't have a definite shape. So they're not going to compress and shear like that. So our displacement notice our displacement down, our displacement up, but the energy goes that way. Now we said that they only go through solids. There is an exception to that. Light. Light actually is the one wave that doesn't need any medium. It's the one wave that does not need any medium. Waves need a medium to carry them. I needed a spring to carry the energy. We need air to carry our sound waves, things like that. Light does not need a medium because light is not one wave. Light is two waves. You have two waves working together. You have an electrical wave going one way, and you have a magnetic wave going the other way, and they're self-propagating. In other words, this magnetic wave creates an electrical wave, which creates a magnetic wave, which creates an electrical wave. So it's a self-propagating thing. That's why it's called an electromagnetic wave. But light is two waves. That's why it doesn't need a medium, because it self-propagates on that. So although light is a transverse wave, and you can write that down, that light is a transverse wave, it's actually two transverse waves that work together on that. Questions about transverse waves? Yes, sir. Pardon? Oh yeah, if I pulled it out that way, it would have worked any way I pulled it. But still, the medium is going to move in a transverse to the motion of the energy. Oh, where am I? Somehow, I lost...